afternoon, everybody. I hope you're still awake and with us. Welcome to The Beast Within, Evading Dynamic Malware Analysis using Microsoft COM. This is Mandalay BCD with Ralph Hund. Before we begin, just a couple of notes. You've probably heard these throughout the day, but you should make sure you stop by the business hall, which is downstairs in Bayside AB. The Black Hat Arsenal is on the Palm Foyer upstairs on level 3. And of course, the Arsenal reception is today at 5 p.m. If you haven't picked up your merchandise at the Black Hat swag store and bookstore, this is your last day to do it. So go by before they close and get your swag. Also, be sure to visit the Kali Linux Lab, which is right over here in Mandalay Bay A. Thank you for putting your phones on vibrate for the term of this talk. We really appreciate your cooperation. And without further ado, your speaker.
Okay, so thank you for the introduction and welcome to my talk, The Beast Within, Evading Dynamic Malware Analysis using Microsoft COM. My name is Ralph Hund. I'm one of the co-founders of the Germany-based company VMware. And basically during our testing, we identified that there is a certain category of malware which seems to be pretty interesting to take a look at, because we saw that this particular category of malware, which is malware that uses Microsoft COM explicitly or implicitly underneath, it seems to pose a lot of problems to analysis systems. And this may leave people with a false sense of security, because if they look at the reports that are generated by such systems, then some stuff, for example, just isn't in there, or other stuff just doesn't look like you would expect it to be. I am here today to talk about this issue, to present our findings, to explain where the problem underneath is, and also to propose some mitigations. So the talk is basically structured in 4 different sections. At first, I'm going to give an introduction on all of the relevant topics. Then in the second section, we are going to talk about different case studies, which are basically test cases that we created in order to test the efficiency of analysis systems. Then after that, we will basically proceed to more or less the heart of the talk, which is the third section, in which we are going to talk about how these analysis systems are designed and where the problem lies underneath. And then finally, I'm going to have some slides about an alternative approach that should mitigate these previously mentioned problems. Okay, so we're going to talk about dynamic malware analysis in order to understand what dynamic analysis is and why it has become so increasingly popular over the course of the last years. You first have to understand what problem it tries to solve. And basically there are 2 kinds of problems it addresses. First of all, according to various sources, there are actually hundreds of thousands of new malware files being seen in the wild each day. Of course, that does not mean that there are actually hundreds of thousands of new malware families being seen in the wild. In fact, there is a lot of polymorphic malware that just re-encrypts itself every time it spreads using a new encryption key. And this is why the file always looks different from the outside, and at least the hash has changed. So that's one big thing, one big issue, because if you want to provide security to a network, for example, and you have your different sensors in that network, in an email gateway or in an HTTPS gateway, then you have to look at all these files and you have to make an assessment as to whether you think that this is a good file or a bad file. So that's one thing. The other thing is, obviously, there has been an increasing complexity in the malware that we've seen. I guess everybody of you has heard of that. So we have nation-state actors that are getting into the malware business for whatever reason. So things are getting more complex. So this means that traditional signature-based approaches, they have their shortcoming, because oftentimes they assume that they can only detect something which somebody has taken a look at previously. And if you have so much malware and so complex malware, usually that's just not the case. Basically, you have 2 routes left which you can go then. First of all, you can do static analysis. This means that you're analyzing a sample file without actually executing it. This is not what the talk is about. We are going to talk about the second route, which is dynamic malware analysis. And dynamic malware analysis means that you are executing a file, you are monitoring its behavior, and from that you draw your conclusions about what this file is all about. Yeah? And the good thing about dynamic malware analysis, for example, also is that if you have enough resources, you can just scale it up, and you can do tens of thousands, hundreds of thousands, if not even millions of analysis each day. And also you don't need to know anything about the sample beforehand. So this is basically why it greatly helps you in solving these 2 different problems. When we talk about dynamic malware analysis, we basically mean sandboxing, so I will just use the term sandboxing for the rest of the talk. And as you might know, there are different kinds of sandboxes out there. There are academic ones, a lot of commercial ones. In the end, they always kind of work the same if you look at it from a big picture. This means that usually you have different sample types that are supported by the sandbox. And if you want to analyze such a sample type, such as a Word document, you submit it to the sandbox. Then the sandbox creates like a virtual machine. And inside that virtual machine, that Word document is being opened. For example, this could be like a malicious Word document that contains a macro. And that is being opened inside that virtual machine. And then the system just runs for 1 or 2 minutes. During all of that, there is a monitoring engine inside the sandbox. And this monitoring engine tries to understand what goes on in the back. So, for example, if that macro creates a new file or it sets up a network connection to a remote server, then this would be something that the monitoring engine wants to see and wants to log. After these 1 or 2 minutes, the entire system is just shut down and reset. And out of these logs, different kinds of reports are generated. As a manual analyst, you can just look at these reports and draw your conclusions about what the sample is all about whether it's a good or a bad file, and why it is bad, for example. This is one use case. The probably more important use case is that the sandbox itself can like automatically detect certain kinds of behaviors out of these logs. So, for example, it could detect that a file was downloaded from a remote server, and then that file was written to disk and then was executed in the background. And this is a certain kind of anomaly or behavior that is very like distinct for malicious files or malicious macros, because why would you want to do something like this, something like that, unless you are having something malicious in mind? So with these different kind of behavior detections, the sandbox can then, in the end, better understand what's going on. And in the simplest case, at the end, you get some sort of traffic light or so, which tells you that I think this is a good file, or I think that this is a bad file, and then you can just block it or pass it on. This is basically how every sandbox works. The only thing that's different is like the technology underneath. But from a very big picture, this is just basically how it works. Okay, so let's have a small look into Microsoft COM. Microsoft COM stands for Microsoft Component Object Model. And what it is basically it is a binary interface standard for software components. What it tries to solve is, imagine you have 2 different applications in the Windows world that would usually be binary applications, and these applications want to talk with each other, they want to access the other's functionality. Then it makes sense to have some sort of standard in between, so some sort of standardized interface, so that if you want to call the functionality of the other application, you do not need to know any of the internals of that application. You just follow that standard, and then you know it'll work. And this is basically what COM is about. And the idea behind that is that you can have different applications written in different programming languages, and they can just talk to each other if they just stick with the COM standard. In the end, what it basically is, it's more like an extension to what the C or C++ standard already standardized. Since C and C++ was basically developed by Unix people, they did not put a lot of effort into standardizing stuff on the binary level, which is more important for Windows, because in Windows you usually have like compiled applications and you do not have the source code of applications. And this is where COM just basically comes into play. COM allows you to even provide an like object-oriented API. And this means that usually if you provide a COM interface, or if you provide a COM API, then you have different COM objects with different interfaces and methods. So interfaces are usually written with a capital I prepended. Over here you can see that the iWeb Browser 2 interface, this is basically an interface that is provided by the Internet Explorer. And these interfaces, you can think of them just like classes in C++ or in Java. And they have different methods, such as in this case the navigate method, which can then have all kinds of parameters. Yeah? Interface names and methods are typically separated using these 2 colons. Microsoft COM is actually a very old technology. So I think Microsoft started developing it back in the late 80s when Windows 2.0 was like the current operating system. Nevertheless, it is still used as the foundation of many current technologies in Windows. So DirectX, for example, makes heavy use of COM. Windows Scripting Host, which is the execution engine in Windows that executes JavaScript or Visual Basic script files or Visual Basic for applications. The runtime of that makes heavy use of COM underneath. Such does Microsoft Office, because if you execute a macro, that is being executed inside that Windows scripting host. So there is a lot of COM fanciness going on underneath. And basically the same also goes for the runtimes of PowerShell and .NET. So why is that interesting, especially for malware? Very recently, we've seen these different ransomware waves. And interestingly, what the people, like the way they infected PCs oftentimes was by using file formats such as Visual Basic Script, JavaScript, even like obscure file formats such as HTML applications. And it seems like people are just shifting away from using executables in order to infect other systems. They're just using these kind of systems because oftentimes like spam filters, they do not deal with them pretty well, so on and so forth. So it's definitely, we would definitely say that, you know, with the exception of DirectX, all of this is very relevant for malware analysis. In our malware corpus, we basically looked at the different interfaces that we see malware using. And these are mostly interfaces that are already provided by the operating system. So Windows itself provides a lot of COM interfaces that you can use to do all kinds of stuff. What we see a lot of times is that malware uses the Internet Explorer interface that I talked about previously. And it basically works like this. So you can remote control an entire Internet Explorer that is hidden in the background of the system using that interface. And then you can just tell it to download a file from an arbitrary URL. And that's pretty cool because, for example, you can use that to bypass application firewalls because the network connection comes out of an Internet Explorer process. And oftentimes application firewalls will just say, okay, well, I'm fine with that. It's just the Internet Explorer. So that's pretty common. What we also see is the shell link interface, which is being used in order to create shortcuts, for example, in the autostart folder, but also to delete the files on the file system, to modify existing files, so on and so forth. Another interface is the Windows Management Instrumentation Interface, WMI. This is basically a system that exists inside Windows that allows you to do all kinds of stuff. And malware, for example, uses it to query for any installed AV products, which is very easy to do using WMI. Then there's another interface, the Firewall Manager interface, which basically allows you to create new firewall rules and therefore firewall exceptions for your program. There's a task scheduler interface that allows you to create new tasks. This is oftentimes used to gain persistency in the system so that the malware is being started after reboots and so on. What we also did is we basically have different sample sharing programs with partners, and we kind of looked in a lot of samples that we get from these sample sharing programs in order to understand how many samples actually use Microsoft COM at some point. And we could see that around 20% of the samples that we get there actually use Microsoft COM methods at some point, which is actually more than we expected because nobody really talks about this issue. So the sheer fact that every fifth sample just uses Microsoft COM at some point is kind of interesting to us. You have to say that it very much depends on the sample type that you analyze. So for executables, it's not so common to have some COM stuff going on in there. However, for example, for malicious Office documents, which are almost always using macros, as I said, it's very common to have some COM stuff going on underneath because the runtime just makes heavy use of COM. So in the end, you can just think of it that I just want to mention that there are like tons of other interfaces that also exist in the Windows world that you could use, and you can like easily write an entire application in Windows that only accesses COM interfaces and doesn't access any normal API, so to say, and still does whatever you could think of. Like you can create arbitrary files, access the registry, download data from wherever you want, so on and so forth. Okay, so what we did is basically we wanted to find out how good do sandboxes perform when analyzing COM malware, and for that we didn't want to use real malware because with real malware you never really know if the same thing happens again if you analyze it again because for some reason a CNC could be down or sometimes it just acts differently. And for this reason we just basically created test programs, test cases, which are very small programs, 10 or 20 lines of C code, and they basically do what malware would do, and then we could just use them for testing, and because we definitely know what they're doing. So we created 5 different test cases, and these were inspired by the typical malware behavior. So, for example, malware typically tries to gain persistency in the system. It tries to contact a remote host for downloading the next stage or for receiving some commands. It tries to evade any existing analysis system, so on and so forth. The 5 test cases that we created are, first of all, an autostart test case. This is a small program that creates an autostart entry using the CLS-ID shell link interface. CLS-ID stands for class ID and is basically a unique number that identifies every interface that exists in the COM world. The second test case is what we call the browser test case. It uses that previously mentioned Internet Explorer interface in order to contact the remote server using an encrypted connection. The third test case is a firewall test case, which only disables the entire Windows firewall by accessing the COM interface of the Windows firewall. The fourth test case is the file system test case, which copies itself into the Windows folder using the so-called file operation interface. And then finally, we have the new process test case, which it basically forks itself, so it creates a new process of itself using the WMI interface, because for whatever reason that is possible with WMI. Okay, so what we then did is we took these different test cases and we submitted them to different sandboxes that we could get access to. So for example, we used one open source community sandbox, also one public version of a commercial sandbox, and 2 other sandboxes. We basically used default configurations for all of these so that we could be sure that we're not misconfiguring the system. Okay, so let's just have a small look at the detection results. First, you could see that the first sandbox, which was the open source sandbox, doesn't perform too well. So if you take a look at the reports that are generated, you're not going to see anything of what the test cases actually do. Although we could still see in the screenshots that the test cases were executing correctly. So they were exhibiting their behavior, but it was just not part of the logs. At this point, we don't really know why that was the case. There seems to be an issue underneath, and we didn't have the time to look into it, but we just have to accept that. So it definitely doesn't perform too well in here, obviously. So for the other sandboxes, let's just go from the left to the right. In case of the AutoStart test case, all of the sandboxes detected that, and they had that in their logs, and everything is just all fine. In case of the browser test case, it was kind of like that, and by kind of I mean that you could see inside the reports that a remote host was contacted and that there was probably an HTTPS connection, but what you couldn't see, for example, is the URL that was being accessed. You also couldn't see the data that was being transferred. And oftentimes you want to have that data inside your reports because it helps you in creating whitelists, blacklists, and so on. So nevertheless, it's still okay. So at least you could see that a network connection was being made. We assume that it is probably due to the case that they are just parsing the network dumps at the end. And this was an encrypted connection, and because of that, you can't find out the URL because it's encrypted data. Okay, so the third test case, which is the firewall test case, for that, only the last sandbox actually had that in the reports. All of the other sandboxes had like no entry anywhere, which is bad, definitely. For the fourth test case, it's kind of like that again, except that the third sandbox, if you look at the report, there's basically like a copied file sections. And inside that copied file section, there's nothing in there. So it didn't understand it at this point that the file was copied. However, if you look at a low-level report, you can actually find one log entry inside that low-level report that indicates that that file was copied to the Windows folder. So it somehow sees it, but it doesn't really interpret it right. Yeah, I mean, you would assume that if you're analyzing an unknown piece of malware, then you're not going to look into that low-level log because it just contains hundreds or thousands of lines of code, and the probability that you will find that one single line of code that is relevant is really low. So it's more of an X than a check mark at this point. And then finally, we have the new process test case, and again, only the last sandbox detected that, so to say. The other sandboxes didn't realize that there was actually a new process being created. And at this point, you have to understand that this is kind of like a worst-case scenario, because with sandboxing, what you do is you never monitor all of the processes in the system. You start by monitoring the first process, for example, Word, and then if that process creates a new process, you also monitor that process, or if that process injects into another process, you also monitor that process. And that's how it works. This also means that if you don't understand that a new process is being created by your monitored process, then you're not going to monitor it, and everything that happens in there is not part of the logs anymore, right? So you can do whatever you want, and the only thing that you can have is have some sort of fallback mechanisms that work on the network dumps or so in order to find out stuff. But this is definitely not what you want to have. So you definitely want to understand that something like this goes on. Okay, so if you just take a look at it again, how could we interpret the results? It looks like the last sandbox is the best one. It didn't get evaded, so it only had like small problems with the second test case. And you could say that, well, that's the best sandbox. The other ones, they just have implementation flaws, and somebody has to go there and fix them. But it turns out that it's not quite like that. And that's for the following reason. Noise. If you look into the reports of these sandboxes, you will see a surprising amount of noise. And by noise, I mean behavior that is in there, but that's not actually part of the test cases. So as I said, the test cases are pretty small programs. And if there's something in there in the reports which is not part of these 10 or 20 lines of code, then that's basically noise. For example, with Sandbox 2, you could see that there are a lot of wrong IOCs in the reports. IOC means indicator of compromise, and these are basically host names or files that were accessed during the analysis by the sample. And then there's stuff in there such as like Microsoft.com, but also other IPs and other host names which are just not, we just never access them in the test cases. So that's not good because it increases your false positive rate, and it also makes you draw wrong conclusions. For Sandbox number 3, it was a bit worse. Actually, the behavior detections that it has actually detect stuff such as anti-reverse engineering, which is interesting because we do not have any anti-reverse engineering inside our test cases. So why is it part of the logs? It also detects stuff such as suspicious imports, and these are imports which we do not import. They also have nothing to do with COM, they're just there, and yeah, it's kind of, the question arises, where does that come from? And then finally, if you take a look at the last Sandbox, which performed by far the best, it basically contains of a report. It basically has a report which contains of 136 events. An event is something like a file was accessed, a process was accessed, but also a certain behavior that was detected. And if you just go through that and you try to extract these events that are actually related to what the test cases do, and even if you're not strict in doing so, you will come up with a number such as 32. And this means like almost 80% of these events are noise. It's just stuff that's in there, but that's not really part of the test cases. You know, files that were accessed, which are not part of the test cases, hosts that were accessed, which are not part of the test cases, so on and so forth. It also has detects behavior such as a TCP port was opened, code was injected into another process. Again, none of that is part of the test cases. Also, it detects that the Explorer process was tampered. This basically means that malware sometimes does that in order to do whatever, for whatever reasons, but we just do not do that in the test cases. So it seems like the better the sandboxes perform, so to say, the more noise they have inside the reports. And yeah, we thought that was kind of interesting, so we took a closer look into it and tried to understand why this is actually the case. So, in order to understand where that effect comes from, you basically have to understand how sandboxing works in the inside. So let's just have a small excursion on the different approaches that you can take in order to create a sandbox. The core of each sandbox is basically that monitoring engine that I talked about previously. And when it comes to that monitoring engine, there are basically three approaches that you can take. First of all, what you can do is you can do hooking. Hooking means that you install hooks at various locations inside the system that you analyze. Usually that means overriding code of the operating system, but you could also override certain data pointers. And the idea behind that is you just, for example, you override code so that every time an interesting operating system function is called, such as the function that is used to create a file, that hook is triggered, and then that hook detours into your monitoring engine, and then your sandbox understands that that file was created, and then you can just log that, put that into your logs. Yeah? And then after that, it'll just jump back into the actual code, and everything just looks at it as if it was just, as if nothing of that happened, so it's transparent. The advantage of that is that it's quite fast because you can analyze the program on real hardware using virtualized system with hardware virtualization on. That's the advantage. The disadvantage is that it can be detected because malware can detect that these kind of hooks exist inside the system. Then the second approach is the emulation approach. The difference in that is that you're actually emulating the entire system in which you do the analysis. And this includes every hardware device, so including the main CPU of the system. Yeah? This has one big advantage with it, which is that you do not need to place hooks anywhere in the system anymore. Also, it's quite powerful because you're in control of everything. When you're emulating the entire system, you can even see machine instructions and so on. So it's quite powerful. That's the advantage of this. The disadvantage is that it's very slow also because for emulation, of course, comes with a great performance overhead. So you have to somehow deal with that. There's also a third approach, which is the transition-based approach, as I'm going to talk about this in the very end, so I will just skip that over here. So the vast majority of systems actually use hooking. which is why I will just confine myself to hooking. There are also emulation-based systems, but if you're using a sandbox and you don't know whether it uses hooking or sandboxing, then chances are very high that it actually uses hooking. Okay, so just sit back and now try to think of the different design goals that you would come up with if you try to create such a sandbox. And I just basically put 5 different points on here, which is something that we, some design goals that we think are interesting or that we found to be interesting during our development. First of all, no evasion is obviously important, and by that I mean you don't want the sample that you analyze to create new processes without you noticing it. So you just want to have all of the behavior inside your reports. Secondly, no noise, although no noise is a bit of an exaggeration actually. So sometimes you just will have noise inside your reports. It's hard to do without it, but nevertheless you do not want to have too much noise in it. So you don't want to have like 90% noise or so in your report, because again that just leads to higher false positives, lower true positives, to drawing wrong conclusions, so on and so forth. Third point is stealthiness. You don't want to leave a big footprint in the system, because then it's easier to detect you. Stability is obviously an issue, as with every software. In terms of hooking, that oftentimes means that if you're using code overriding in hooking, then so for technical reasons, sometimes it just doesn't work in rare cases. And if in this case the hook is being triggered, like the entire system can crash, and that's bad because then you don't have any analysis anymore. Finally, performance is also important, and by that I mean that you don't want to slow down the system so much so that in the end you're not going to see the relevant stuff anymore within the short time frame that you have. Okay, so I'll just go ahead and say that goals 3, 4, and 5 can only be achieved by limiting the amount of hooks, and that's for the following reason. If you have too many hooks, then you're not going to be stealthy anymore. It'll be easier to detect you. You will also probably run into stability issues if you have too many hooks, because the more hooks you have, the higher the chances that something goes wrong and the system crashes. And finally, performance also, because the more hooks you have, the more detours are being taken during the execution, and every detour imposes some sort of performance overhead. And if you have too much of that, then you will run into problems. Okay, so let's think about one of the main challenges that you will have when that still remains open right now. And this is actually, where do you place your hooks inside the system? This is like the main decision that you need, that you will make. And it turns out, like, the more you think about it at this point, that there is not too much room for decision making. And this is for the following reason. So imagine that you're analyzing a malware, and that malware wants to create a new process. This is definitely something that you want to detect. So in order to create a new process, you can call multiple or various different functions inside Windows. You can call officially documented functions, such as create process, for example. There exist different types of that. There also exist a lot of other functions inside Windows, most of them for backwards compatibility. Others exist for rare corner cases. This is not a full list of the different functions that you can actually use to create a new process. There are many more. It's just to show you the problem. So if you want to place hooks and you want to understand that a new process is being created, for example, you could hook all of these different functions, but then you would have to have a lot of hooks. What is also the case is that instead of these official API functions that exist inside Windows DLLs, you also have internal functions. For example, create process functions usually map to one function called create process internal. This exists inside kernel 32. And it is an internal function. It's not documented officially by Microsoft, but you can still call it if you want to, right? Normally you would never do that because it breaks compatibility with future versions of Windows, and it's a very bad programming style to do that. But if you're malware, you do not care about conventions, and so why not just call it directly? Because if somebody only hooked the other functions, then he just got evaded, right? So we actually see that happening a lot of times. A lot of malware just calls these internal functions directly. What they even also do, and which is more problematic, is that sometimes they actually do not call these functions directly, but they will call like the second or third instruction inside these functions. And that can actually lead to quite some problems, because if you place your hooks in the first instruction and the malware just jumps over it, then either you get evaded or the system just crashes because it just jumps inside your hooked instruction. So this is also an issue that you have to deal with. What you see here is basically what I just call during the presentation, I just call this the first layer of Windows API functions. This is where all of the officially documented Windows API functions are. After that, there is also a second layer of API functions, which is the NT-DLL layer. This is one DLL file that exists in every Windows process, and it's basically a very condensed API, so it's much smaller than the first layer API, and a lot of the functions in the first layer, they oftentimes map to like the second function to reduce code duplication, or they just call some other functions on the second layer. And in case of creating a process, there is a function called nt-create-process or RTL-create-process, whatever the name is, and that is being called at some point. But of course, what you can do as a malware, you can just call these functions directly, and this means you also want to hook these functions, because otherwise, again, you got evaded. And then finally, inside NT-DLL, a syscall is done inside the kernel, and then the kernel actually handles that create-process request. But what you can do also as well is you can just do that system call directly inside the kernel. And then you just jump over the entire user mode thing. So I hope the idea of all of that got clear. The thing is just simply, there are so many different ways with which you can create a process that it's really hard to put a hook in all of these functions, right? And the same problem exists for a lot of other situations. For example, if you want to create a file, there are also tons of functions with which you can create a file, so on and so forth. So what will you do in the end? In the end, what you will do is the only reasonable thing is to place your hooks in the lower layers, because the lower layers, they're just condensed. And the idea behind that is that, well, if something interesting happens, if somebody wants to create a process, at some point it'll end up in a lower layer function inside NTDL or inside the kernel. And if I just hook in there, I will see it anyway. So I don't have to bother hooking all of the create process functions. And this is basically how every hooking sandbox works. What you will do oftentimes is you will like hook certain, you will rarely hook stuff in the first layer when you think that's interesting, but that's really the exception. Most of the time you just rely on hooking on the lower layers. Okay, so yeah, another challenge that you have to deal with is you have to handle noise somehow. I talked about that quite a bit, but just one slide in order to explain where this actual problem comes from. So imagine that you hook inside a malware program that does something. So usually that malware will just call first layer functions. Some of them will map to second layer functions, and some of these second layer functions are hooked because they're interesting. And then the sandbox just understands that something happens and logs that. So this is usually what you would expect, and usually what's also going on. But what also goes on, for example, is that sometimes if certain OS libraries are being started or being used in the system, such as WinSock, which is responsible for all network stuff in Windows, then these OS libraries, they will create own threads inside that process. And these threads, they just run in the same process, and they also do stuff. They also just call functions, yeah, on the first layer, on the second layer. And due to the way that hooking works, basically you will also see all of that, because you're hooking inside the entire process, and you will also see all of that. But however, this behavior is not really part of the test of the sample itself, right? Because it's indirectly related to it, but it doesn't reveal anything that's actually directly done by the sample. And this is actually the reason, in the end, why you have all of that noise. So basically, you have just a lot of stuff that goes on inside that processes that you monitor, and in the end, you have to filter out whether that call that you see, whether this is actually related to that sample or not. In case of these OS internal threats, you could handle that probably somehow, but just imagine that you hook inside a process such as Internet Explorer or Microsoft Word. These are just super complex applications where a lot of stuff goes on, and you have to filter out what's relevant to you or not. So you have to understand whether this call comes from the macro that's being executed, or whether it comes from the GUI or not. And that's really hard to solve, and this is basically why you have that kind of noise inside the report. So thirdly, yeah, the last challenge that remains, I just wanted to have one slide on this, is basically sometimes if you're monitoring in the back of the system inside NTDLL, then certain functions will not be seen, because some of them are already dealt with at the first layer. Simple functions such as get the current date, they do not map to second layer functions. And if you don't monitor or hook them directly, if they are called, you will just not see that. And sometimes this could be interesting because, for example, the malware could only run on February 2nd or so, and sometimes it's just good to have that kind of information. So you have to make a decision as to whether you want to monitor that function too or not. Interestingly, also the exact opposite problem exists, and that's for the reason that these different layers, they work at different levels. So the first layer is basically a high-level layer, so to say, and the NTDL is more a low-level layer. Imagine that the malware calls a function that just downloads a file from a URL. right? So these functions exist in Windows. Downloading a file involves a lot of subtasks. It means that you have to resolve the host name, you have to set up a network connection to that host, you have to send you a query to that host, you have to read all of the returned data from the network, then you have to create a file locally, and then you have to write all of that data to that file. And that's quite a lot of stuff. And the thing is, due to the way it works, in the lower layer, you will only see these subtasks. So you will only see that a host name is resolved. You will only see that a lot of write files are being done, or a lot of receives are being done. And it's kind of hard oftentimes to understand what is going on the big picture. Because it's a more valuable information to know that a file was downloaded, other than there were thousands of calls to write file, right? So yeah, sometimes again you have that what I call the avalanche effect, and you have to understand how you want to deal with all of that. Okay. So what does all of that have to do with COM? So first of all, you have to understand that due to the way that COM works, it is basically an additional API layer that's being introduced into the system. So COM interfaces, they usually work on a higher layer than the first API layer. That's just the way that COM was designed. So you can just think of it very simply that there is this other layer of stuff that exists inside the processes. And if malware uses it, this will just make all of the aforementioned problems worse. Because first of all, you will have to filter out even more noise that is being generated due to that higher level of COM interfaces. Secondly, you will have even more calls that go unnoticed on the first layer because they're just handled inside the COM implementations already. And thirdly, that avalanche effect that I talked about is even worse because you will just have more of these functions more of these subtask functions, so to say, that are being generated. So that's already pretty bad, and basically explains a lot of the stuff that I talked about previously. But this is actually not the biggest problem. The bigger problem is like the second issue, which is COM support stuff such as RPCs. RPC stands for Remote Procedure Call, and it means that if you call a method inside your process, it doesn't mean that this method is actually executed in your process. You can actually let it be executed in a completely different process inside the operating system. Yeah? And this basically works the following way. So just imagine that you analyze a malware that wants to create a new process using that WMI interface that I mentioned previously. So what it can do is it can just initialize COM and say, okay, I want all of these method calls to be executed as RPCs. And then it just does the method call. And what will happen is that there will be something such as a COM proxy interface inside that process. This is more or less like a small shim. It just receives that COM call, and then what it does is it marshals all of the relevant information, such as the interface name, the method name, and the different kind of parameters. So all of that is marshaled into a big blob of binary data using some internal format. And then that big blob of data is sent to the COM server process that should handle it using an RPC. Yeah? So RPC is a mechanism provided by the Windows operating system. So an RPC function will be called that will go through these layers to the kernel. The kernel then knows that which COM server process is responsible for this RPC. And then it will just deliver that big blob of binary data that it doesn't understand. It just knows that it's some data, and it will just deliver that to that COM server process. And over there, the entire data just goes back the other way and is being unmarshaled. Yeah? In this case, there will be like a COM implementation inside that COM server process, and this will actually then execute the method, which is it will create a new process. So why is that problematic? The problematic thing is, as I've said, in sandboxing, you do not monitor all of the processes. And what a lot of sandboxes do usually is you have a fallback mechanism that just says, okay, if a new process is created in the system, then I just look what was the parent process of that newly created process. And if the parent process was also monitored, then I will monitor that process, right? So this is a very easy way in order to monitor all relevant processes. However, it does not work in this case because the parent process will be the COM server process, which is not monitored. It's just one operating system process that just exists for some reason. And this is actually the reason why all of the other sandboxes, except the fourth one, got evaded at this point, because that new process is being created out of a COM server process, and if you don't understand that this is going on, you just got evaded. So how could you deal with that? The more you think about it is that, very simply speaking, the problem is right now, imagine all of that goes on and all you see is basically what happens at the NTDLL layer or inside the kernel. Yeah, so you're basically just going to see the fact that there is an RPC. You will see a big block of data, of binary data in an internal format, and you you don't really know what's going on here. You don't really know what method is being called, what are the parameters. And that's actually really hard to find out because the thing is, all of this is internal information. If you wanted to interpret this big blob of data, then you would need to know a lot of the internal stuff that goes that happens inside COM. And believe me, COM is like super complex. As I said, it was created in the 80s, so it still has support for all of the backwards compatibility stuff, and it's being used all the time. So you would have to reverse engineer basically all of that. And actually, it is even possible for the interfaces to decide themselves how stuff is being marshaled. So some interfaces, they just have a custom marshalling, and you would have to understand that for every interface. And that's really a lot of work. And then, like Microsoft or the implementers of these interfaces, they're free to adjust anything anytime they want. So this is definitely a very, very tough road. And I don't know anybody who went this road, and I doubt anybody who ever will, because it's just very complicated. So what still remains then is that, well, as a fallback mechanism, what you could still do is, like, even if you don't understand what COM method is being called, you could just simply say that, okay, I see that an RPC is being done into another process, so I can just monitor that process. I could just monitor that COM server process, and then, I will also monitor that new process. But then the problem is, how do you filter out all of the noise that happens inside that process? If the COM server process is an Internet Explorer, and this happens to be the fact if you're using the COM interface, then you will see all of the behavior of the Internet Explorer in there. And how do you filter all of that out? The same goes for Microsoft Word or so. This is one big problem. And secondly, what can also happen, and what actually does happen, is there are other processes in the system that are not monitored, that are part of Windows, and they do the same COM method calls at the same time, and they are handled in the same COM server process. So you would have to understand, you would have to filter these out too, because you don't want to have that inside your reports. So, in the end, what I want to say at this point is simply that the more you think about it, the more it kind of becomes obvious how hard it is to solve this problem, because you basically have two routes which you can go. First of all, you can say, like, I'm just not dealing with all of it, I just ignore it. Okay, that's fine, but then you got evaded. The second one is that, well, I'll just try to monitor as much as goes on inside the system. You could do that as well, but then you have the problem that you will have so much noise in the system because you're monitoring so much stuff. And with all of that in mind, if you just take a look at, if you take a look again at the noise that we had in the last sandbox, first of all, you could see that it says it opens a new TCP port. Actually, this is not something that's done by the test cases. However, this is something that happens inside the Internet Explorer COM process at some point, simply because for internal reasons, it just opens a TCP port. And it seems like the sandbox detects this, and as I said, it's hard to understand that this is actually not part of the samples. Secondly, code injection. Again, that was detected, but not done by the test cases. However, the COM runtime does RPCs, and doing RPCs can be used for code injection in some points. So some malware uses that, but this is not what is actually going on here. And it seems like the sandbox just misinterpreted that as RPCs. So, and again, it's really hard to find out whether this is a real code injection or not. And basically the same in the end goes for the Tempest Explorer noise that was found. And in that case, it's just that forced test case that copies itself to the Windows folder. What it does is it does an RPC, and this RPC is executed in a Windows Explorer process. And it seems like this made the sandbox believe that actually the test cases, they tamper with the Explorer at this point. But again, that's just not really right. So, yeah, so, yeah. The thing right now is when you think about it and think about where the problem lies, then one solution that might help you a lot with fixing all of these problems, or fixing them even by design, would be that instead of seeing or of monitoring the samples in the back in these lower layers, if you would understand what happens in the first layer, so if you would understand which COM method was being called in the very front, then you wouldn't have these kind of problems. So what you could do is, for this case, you could use emulation, but in our case, for various reasons, we just experimented with other stuff, and what we came up with was another approach in order how we could do that. So, and this is basically what we call intermodular transition monitoring, and I'll try to explain how it works on this slides. And basically, the idea behind that is that you just monitor the execution of something without using hooks, only by making use of how the MMU works. Yeah? So you're modifying the MMU data structures, and by that you understand what happens inside the process that you monitor. And that's pretty cool because it's totally transparent, and it even works out of a hypervisor. So the idea that is now is the following. So imagine that you have a process that you want to analyze. What you do is you split that process in two different memory sets. First of all, you have one set which is executable, and all of the malware code is being put into that set, so it's marked as executable. This means that the instruction pointer can just execute code in there. And then all of the other memory is then being marked as non-executable, right? And that means that if you start the program, the malware, then at some point it will call some COM interface or some other API. This will mean that the instruction pointer jumps into the non-executable region, and then this generates an exception in the system, because this is a non-executable region. An exception is generated, and then your monitoring engine can come into play. It can understand that, and it can actually read out all of the relevant data. So it can read out what interface was called, what method was called, and what are the parameters. The thing is, right now, all of this happens at the standardized COM layer. So this is completely different to reading out that data back in the RPC, in NTDLL, because all of this happens at the layer which is standardized by Microsoft. So if you go through the official standard, you know where you have to read out the interface names, the method names, and the parameters. So after that, what you then do is, and that's the trick now, you just switch both sets. What's been executable before is now non-executable, and what's been non-executable is now executable. And then you just let the system run. You don't care about what happens then. It's just some OS internal stuff will happen, and at some point, the instruction pointer goes back when data is being returned, and then you just do the same thing all over again. Yeah? So you just constantly switch between these two sets, and by doing that, you understand what happens like in the front of the system. You will see every first layer API call, every COM interface call, and you don't even bother about what happens after that, right? Challenges that still remain for us at this point, just to give you some idea, was that you still need to pass a lot of information. So you still need to pass out the like method names and so on and so forth. And that's quite complex because there exist a lot of different parameter types and so on. And nevertheless, it's like a finite list, and you can just go through it. And as I said, it's standardized. Then there's stuff such as dynamic binding of COM interfaces. I would just skip over that because it's very technical. It basically means there are different ways in which you can call a method. So you just have to be aware of all of the different kinds. Sometimes you also have to understand what each COM method does. So you have to understand that a function is being called that creates a new process using WMI, for example, because then you want to monitor that new function. So you have to have some sort of a semantic understanding, and therefore you have to go through the existing COM interfaces. That's quite a lot of work, but it's doable in the end. So you just have to go through it once, and once you've done it, it'll just work in every case. Okay, so to summarize, this basically fixes all of the aforementioned problems, because if you see what happens like in the front, actually, if you're analyzing an executable, for example, you won't have any noise anymore by design, because you will only see what the malware itself does. You're not going to see what any other threats do, because they will be inside the OS library. So there will be no noise. Yeah? If you're analyzing script files, you will basically analyze the runtimes of these script files, and then you have some noise, but it's way less than with lower layer hooking. You will also not miss any first layer calls by design, because you're just seeing everything that happens on the first layer. You're not going to have that avalanche effect anymore for the same reason, because you just see everything at the first layer, so there's no avalanche effect anymore. And finally, there's no need for special handling of RPCs anymore. You just do not have to deal with it anymore. You just don't care about the implementation of anything, and it'll just work. So, yeah, so that being said, that's basically all I had to say, and yeah, I would like to thank you for your attention. So I think we still have maybe time for one or two questions left. So, yeah. I will just repeat the question if you want to. It's okay.
So the Intel MMU thing, does it work if you have two threads that do things concurrently? So you have one thread that's executing in malware and one thread that's executing in Windows DLL? Does it work?
Doesn't work because the MMU is per CPU, and if they are in parallel, we will have two different sets, and this is why it works. So,
okay, thanks.
Yeah.
I want to say one more thing.
Yeah.
The open source sandbox does work with the process following. Thank you.
Okay, I haven't understood the last thing, but okay, it's fine. Okay. Okay. So if there are no questions left, if you still have anything you want to discuss, you can just come to me. I will just be outside of the room. And yeah, again, thank you for your attention.